So anyways, let's try to rebuild this entire thing. Telnet. Holy shit! Alright, so can I connect another one? Telnet. Boom. And look at that. 0% CPU. Single thread, 0% CPU, asynchronously handling several clients. Look at that. Everything is fucking working. I can even close them. They're closed automatically. Everything is fucking working. How about that? Are you happy now? Are you happy now? People have been hating me for, you know, you're spinning, you're doing it incorrectly. Now I did it correctly. Now I did it fucking correctly. So our asynchronous future library is working exactly as intended. It's efficient, it's fast. We're gonna win over Tokyo. Dub, 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 dub. Who needs Tokyo when you have Kokyo? So, listen chat. So the problem is this. I start my asynchronous echo server, right? Not echo server, but with the H, right? I don't know how to speak English, I'm sorry. So if I take a look at the utilization of the cores, right, so you will find something very interesting. You will find that one of the cores, actually two of them, are like utilizing 50%, but they're like very much, you know, active. Right, and this is because I'm busy looping when I'm polling the sockets. Right, that's what I do. And I did that because I wanted to focus on the design of the API of the library, of my futures library in C3, rather than the exact implementation. Right. And funnily enough, some of you, my fan is started to work because of that, by the way. Some of you reacted, I would even say overreacted to that. Right. So some of you were like shocked, like, holy shit, you are polling, you are busy looping asynchronous stuff in 2024. It's 2025, by the way, so happy new year. In 2024, holy shit, that was their reaction. That was their reaction. It's almost like they saw me using Go2 or something. Right, and because Dijkstra famously said that Go2 is bad, everyone is having a seizure every time they fucking see a Go2. You guys are like babies. I think you just need to grow up already. Right. So essentially, it is okay to write bad code if it is not finished. Because that's the process of making a project. Right. In between, the code is bad. Right. And that's the point. You're taking bad code and you're slowly moving it towards the place where you want it to be. That's how it fucking works. So yeah, so today we're gonna look into what's going on in here, why does it actually consume the 100% CPU, and let's see how we can fix that. Sounds good? Sounds Gucci? Sounds Atamaguchi? Let's fucking go. So, right, so if you take a look at how exactly this thing is implemented, there's this nasty loop, right? So while true, and we just iterate through all of the futures that we have in here, and we just roly poll them. Within those futures, we have read and write operations into the sockets, right? So for example, read once. And essentially when we actually perform the read call on the socket, since it is marked as non-blocking, it returns an error would block in case if it would block. Right, and in that case, we just return the future to be pending. Right, so and essentially what we end up doing is that we end up spinning on this thing and checking, like, would you block, would you block, would you block, would you block? And then when it unblocks, we get the data and do stuff like that. So essentially, CPU is doing a bunch of nothing, essentially. So how are you supposed to, like, circumvent that? So in POSIX and Linux specifically, there's mechanisms, such mechanisms as select poll, right? As far as I know, select is not recommended to use on Linux, all right? So we can take a look at the select. Right, so here it is. It's a pretty big function, right? It accepts like a pointer to file descriptors and stuff like that, right? But it is very much not recommended to use. Right. So because as the documentation says, select can monitor only file descriptor numbers that are less than FD set size, which is 1024, and a reasonably low limit for many modern applications. Right. So it's basically not recommended to be used, and you're supposed to use a poll mechanism instead. Okay, so let's actually use poll instead. Right, let's take a look at it. So there's also epoll, there is also, I think, IO Uring or something like that. There's a lot of mechanisms like that, and all of them, they just like give you more and more and more control over like what you can do and whatnot. So what's the point of poll? Poll waits for some events on the file descriptor. So essentially, instead of spinning in user space, it just goes into kernel space and just are we back? Are we back, Shay? This time, it was not KGB. It was not KGB. It was my laptop charge. My laptop is actually configured to go to sleep at 25%. I forgot to plug in the charger. So, but I mean, luckily it didn't discharge completely, so I didn't have to like a hard reset, you know, my entire laptop. So yeah. All right. So essentially, we didn't have a KGB attack this stream. That means it may actually happen, right? So usually, like these days, when I'm streaming, there's usually a KGB attack, and I have to disable my VPN to dodge it, right? So that didn't happen yet. So that means we can go down one more time on today's stream. So anyways, so we were talking about the poll, you know, the poll function, right? So what it does, it just like you give it an array of file descriptors, right? And you also describe what kind of events do you expect from to happen on these file descriptors, and then it just goes to sleep, right? And when one of the events, one of the desired events happened on one of the file descriptors, the kernel wakes you up and tells you, go check those file descriptors. Right. That way you don't spin yourself constantly checking, would you block, would you block, would you block? It doesn't matter, right? So I'm saying, okay, from these file descriptors, I expect these events, wake me up when that happens, right? And just go to sleep. And that's usually how it is implemented, right? So that's how we usually implement it. Right, so I already like refreshed how to use this kind of thing before. I used it in the past long time ago, then I forgot. Right, on stream I tried to refresh it, so I kind of now remember how to use it. Should we look into how it works standalone on the stream? Right, or should we just jump into implementing that in the library? I think it would make sense to actually take a look at it standalone, like how you use it by itself, like outside of the context of like future library or something like that. So we can go ahead and try to do that. So I think it could be interesting. So let's actually go to C3 foot, and here maybe I'm gonna do something like a poll try, right, underscore try. So this is gonna be C3. I didn't want to create a folder. Okay. Poll try C3. Let's fucking go. Let's import some scheisse stdio. All right, so, and I'm gonna do void fn. It's actually the other way around. And what we're gonna say in here, io print fn. So what we wanna do, we wanna kind of get a gist of how to use this library. So here's the hello world. And we have to add this kind of thing to the project. So let me maybe quickly do that. So I'm going to do C3 project add target poll try. It's going to be executable, and the source code is a poll try C3. Right, it's a poll try C3. So we can also try to build poll try. Right, and as you can see, the program is linked, so we can now try to even run it, and it says hello world. Okay, so let's actually start with maybe creating le socket. All right, so let's create a server socket. Right, so since we were working with the echo server, an echo server, if you don't remember, is basically a server that listens to incoming connections. The client connects, the client sends some data, and the server has to send it back. Right, that's the echo server. It's sort of like a hello world of networking, essentially. Right, so I think we need to do something like net TCP. Right, so this is where all of the cool TCP abstractions in C3 are located. We can even take a look at them. std net TCP. Right, so and the thing we are interested in is a listen function, right? So it creates a server socket. Server le socket. So here is the server le socket. So we're gonna assign it like that, TCP listen. I suppose we're gonna unwrap this error right away, like so, right? So it will crash if it doesn't work. Okay, so host, we're gonna listen on localhost. Let's not listen to any incoming connection, any outside connections. So the port obviously is 6969, that's the port. The backlog, let's actually hardcode it to 69, and so we also need to set some options. I think I'm gonna set reuse address, and that's about it, right? So that essentially creates le socket. We can now even try to run and compile this entire thing just to see that it prints okay, so that's pretty cool. So now you can listen to connections, right? So you can do something like accept. Actually, it's a standalone function, it's not a method of the TCP socket, right? So something like this. And this should give us just le socket. Obviously, we want to sort of crash. And now, if I try to run this entire thing, it blocks, right? It straight up blocks. It straight up blocks. So, and it will only unblock if you try to connect to port 6969. As you can see, we connected to the port and it unblocked, right? So that's how accept works. But it is in a blocking in a blocking state, right? In a blocking mode, I would even say, right? So when you set it to non-blocking, right? So you have to take take a row socket, set non-blocking to true, and obviously it may fail. It will actually immediately unblock, but in that case, it will return you an error, which is called would block, right? So if you try to run this entire thing, it returned an error. Well, it didn't return would block because of design reasons of the standard library, but that's besides the point. As you can see, if you make it non-blocking, it fails. Okay, so if I understand correctly, so specifically the syscall accept. In case of the non-blocking situation, right? So let's actually see how it works. Yeah, okay, so in the syscall accept, there is even a section that talks about mechanisms select, poll, and epoll. In order to be notified of incoming connections on a socket, you can use select, poll, epoll. A readable event will be delivered when a new connection is attempted, and you may then call accept. Readable event. So this is actually rather interesting. If we take a look at the signature of poll, we can even take a look at it. C3 has a wrapper around poll, so we can call poll directly, but it has a convenient wrapper that we could actually use. So if you try to sort of like grab this entire thing, right? So there's something like poll. Let me see. So it should be here. It is. Oh yeah, here it is. So it's just a poll. There we go. So it's a function that accepts a slice of structures poll, right? A slice of structures poll and duration, because poll may actually time out, right? So let's take a look at that. So there's a timeout in here, and if you read about timeout, what timeout does? The timeout argument specifies the number of milliseconds that poll should block waiting for a file descriptor to become ready. So you can basically sleep, but you can also sleep with the timeout. So then you can maybe do something else, right? So between waiting for the events and stuff like that. So that's basically what the timeout is. And what is the poll structure, right? So here is the definition of the poll structure. This one is really interesting. So you provide a native socket. We do in fact have a native socket, right? So, and we have poll subscribers, right? So we do have poll subscribers, and this is an enumeration. It's actually not even an enumeration. It is a mask, right? It is a mask, and through the mask you describe what kind of events you're waiting for the sockets. That's what you do. What kind of events? And what kind of events can you actually do in here? So if you take a look at the poll subscribes, right, so the events are any read, prior read, OB read, and just read. So we have 4 kinds of read and also 3 kinds of writes. Don't really know what's up with that, but if you remember, accept will send a read event, right? It basically sends a readable event. So that means we need to listen for read, right? So that's what we're interested in here. Okay, so and also there is a poll events, and it's a mask. It's actually very much similar mask to the subscribe mask, but it's a mask of the events that actually happened. The way you use this function, and it's really, really funny, you create an array of polls. You fill it up with the sockets you're listening and with the events that you expect from this specific socket, and you leave that R events 0, or you may basically set it to anything, right? It doesn't matter. Then you call poll with that array and timeout, right? And then when it unblocks, the kernel will set this mask, and it will set bits of the events that happened to 1. And if the event didn't happen, it would set it to 0. So essentially, these are two input parameters for the kernel, and these are output parameters. So through this parameter, you actually learn, okay, this kind of event has happened. Right, that's how you use this weird function. It's kind of interesting, isn't it? Right, so let's actually go ahead and try to do that, maybe. So let's go into the poll try. We may even probably create like an array, maybe a dynamic array, right? Sort of like a list, like import std collections list, right? So this is going to be a list of polls. So the question is the poll thingy in net_tcp? I think it's just in net, right? I don't quite remember, but doesn't really matter. So in here is the polls. So in the polls, what we want to do actually in here, we want to push the poll, right? And so where is the struct poll? I want to get its fields. I think these fields are very much important. Okay, thank you, Emacs. Very cool. Thank you, Emacs. Right, so we're going to do something like this. So here is, okay. So here is the socket, and we're going to take the server socket, and I'm not going to set this thing. So as far as I can tell, it will be just set to 0. And events that we're listening to, we are interested in a read event, right? We're interested in a read event, something like this. After that, I think that is basically enough, right? So that is basically enough. We can now call poll, right, with the timeout and stuff like that. And if I remember correctly, the return value for the poll, is actually how many events has happened, on how many sockets the event has happened, right? So on success, poll returns a non-negative value, which is the number of the elements in poll fd, whose are events. The output, parameter, the output field has been set to non-zero. Return value of 0 indicates that the syscall timed out before any file descriptor became ready, and also it may return -1 in case of an error and stuff like that, right? It doesn't really matter. So we actually don't want it to time out at all, right? So we wanted to actually poll indefinitely, and not indefinitely, but until some of the event happens, right? Until some of the event happens. And if I understand correctly, to do that, we have to set the timeout to negative, right? So let me see. Specifying timeout of 0 causes poll to return immediately, even if no file are ready. But this is 0. Negative value. Okay, a negative value in timeout means infinite timeout. Okay, so that's pretty cool. So the infinite timeout. So did I? No, I didn't. Copy. So let's go ahead and copy this entire thing. So if I remember correctly, you have to use polls like array view, right? So essentially it will take the list and turn it into a slice. And let's actually set the duration to -1. And here we're going to have n. And I suppose I'm going to unwrap it right away. And here we can print something like print fn. So d sockets, fired or something, right? So something like that. And after that, the accept should be actually successful, right? After that, the accept should be actually successful. So let's go ahead and try to maybe, run this entire thing, and it doesn't run because this has to be sock, and the poll, we have to accept poll through the namespace net, right? If I understand correctly. So poll event read, it also has to be accessed through the namespace net. And so implicit casting poll events to poll subscribes. So I think it has to be actually subscribe read, right? There we go. So accept still failed. And I think I remember, yeah, okay. So I already checked that. So essentially there is a bug in the wrapper for poll. Yeah, it's kind of funny. Let me show you. So you see, it accepts actually duration. It accepts duration. And one of the possible values for the timeout is -1. But it takes the timeout and converts it to milliseconds. So look what happens to a negative value after converting to milliseconds. Print fn, so we can do something like this. And then if you do print fn something like d time ms, right? So if you try to, yeah, it converts it to 0. Thank you, learner. Very cool. So yeah, there is a bug in here. It's impossible to set a negative value for the timeout because you need these, like, you know, nice wrappers and type safe wrappers with different durations and stuff like that. Everything has to be wrapped around everything, and then you can't fucking use API. I'm sorry. Anyway, so I was actually planning to fix that myself and submit pull request, but I think I forgot. Right? So we'll fix that. Doesn't really matter. So essentially what we can do in this specific case, we can just call this shit directly. We can row dog the PostX API like your mom. Anyway, so let's go ahead and do that. So I think the only two functions in here we need is like actual row, PostX call, something like this, and checking for the OS error, right? So this is basically what we have to do. So essentially we need to take the pointer to the polls in here, right? So what I wanna do, essentially, I want to open the collections implementation of the list. So list, it has a pointer which is the entries. So in our case, this particular pointer is going to be entries. Right, and here is the length, right, so I think it's just a method, right, yeah, it is just a method like this. And in terms of timeout, let's just set the timeout to -1. Finally, we can just set it to -1. So in here, if the result is negative, we should just rethrow the OS socket error. Yeah. It's the NANI operator. That's what it is. So, and I think this will work now. So let's actually go ahead and try to run it. And as you can see, it is blocking. And as soon as I try to do something like that, it will unblock. So just look what kind of stupid shit we've done. We had a perfectly blocking socket. It was blocking and accept. We set it to non-blocking. And now it doesn't block anymore, and it fails because like it would block. So we went and used an advanced PostX API to make it blocking again. Are we dumb? What the fuck is going What the fuck is going on with us? Am I right? Absolute coding. This is truly an absolute coding moment. Holy shit. Absolute fucking coding moment. So yeah. But here is the thing. There is a different, it's different, chat. It is a different thing. So imagine that you have several blocking operations in a row. Right? So you do one blocking read, then another blocking read, then another blocking read, and another blocking like write. So, and you block on this thing, right? So maybe you have like socket 1, socket 2, socket 3, socket 4, right? So you want to do these 4 operations that are blocking, but on independent sockets. So that means you can kind of do them simultaneously, but since they're blocking, you can't fucking do them simultaneously. Like you fucking can't. So, right, so, and you can only do them sequentially, right? And you can't process the socket until they're done. But if you mark them as non-blocking, and then use poll, you can just poll all of the 4 sockets simultaneously, and then once one of them is ready, you do this operation. So essentially, instead of blocking them sequentially, you're blocking them simultaneously, right? So that's basically what we did. We sort of like transposed the control flow. Instead of like sequential blocking, it is simultaneous blocking. That's what it is. That's why it is much more different. So let me freaking see. So we can now try to maybe, you know, make a non-blocking echo server, without futures, right? So just like to get the gist of how you're supposed to do that in a synchronous API, right? And how you're supposed to manage and stuff like that. Right, before we do that, I think we need to acknowledge the subs because people have been subscribing like crazy. So let me see. Thank you so much, Brooklyn Dev, for Twitch Prime with the message Happy New Year. Happy New Year to you too. TestTube 69, thank you so much for tier 1. T-God, thank you so much for tier 1. Lucas, thank you so much for Twitch Prime. Let Dance, thank you so much. Let Dance, thank you so much for Twitch Prime. K364_T, thank you so much for Twitch Prime with the message. Yes, to another month of amazing Zosian content, always waiting for more. Thank you so much. Roberto FS1, thank you so much for Twitch Prime. Elf GSF, thank you so much for tier 1 without any message. So it's pretty freaking poggers. So essentially here we just poll, right, and then we do accept. And here is the thing, right, so we accepted this client, right, and now we also need to set the socket of that client as non-blocking. So that's very much important. So it is non-blocking as well, but it is probably not sending any data, right? It is not sending any data, so that means we need to also poll it, right? We need to somehow poll it. So I suppose the easiest way to actually do that is to maybe like take that client and push it into the polls, right? So since it's an echo server socket, why did I read the chat? So since it's an echo server, right? So that means first operation we have to perform read, and then we have to perform write. So we need to poll it because read might not be ready. So let's actually do polls push, and so the socket, le socket we're interested in is the client socket, right? And events that we're listening, right, are the read events. So we are listening to those things. And I suppose, right, so we just need to repeat the whole thing, right? So we just have to repeat the whole thing, like so. So, and you may say that, this is basically looping again, and the answer is yes, but poll is blocking, right? Everything else is non-blocking, but poll is in fact blocking. That's basically what's going on in here, right? That's basically what's going on. So let's actually do something like that. I think I have, wait, let me take a look. Tabs! Query replace. This is because I copy-pasted some code from Learn Code. He's using tabs. He infected my code with tabs, and that's why my indentation was broken. Anyways. So, right, essentially, now we are sort of in a loop, but we're not busy looping because the poll operation is blocking anyway. Right, so it's blocking anyway, so it's totally fine. Trust me, chat, trust me. But here's an interesting thing. So as soon as it's unblocked, we were trying to do accept, right? We were trying to do accept, but we're now waiting. We're now roly polling on two sockets. And who said that the socket that is going to fire up is going to be the server socket? What if it's the client read socket that is fire up? How the fuck do we even distinguish them? How the fuck do we even distinguish them? Well, so I suppose what we can do, chat, what we can do, we can just iterate through all of the polls in here and check if their socket is either server socket or not a server socket. And that way we can kind of know what kind of socket has fired up and stuff like that. So let's go ahead and do that. So I'm going to do for each poll, right? So polls, we talking about polls a lot these days. Kurwa mać, ja pier... I'm sorry. Yeah, so we're iterating through polls, and the thing here we can do is poll sock actually socket, right? And if it's equal to the server sock, only then we are trying to accept that specific thing. And also look at that. This is kind of interesting. Look at that. We are pushing a new client in here, effectively extending the very vector we are iterating. Damn. The rule number one of std vector, as far as, like, if you know, right, is essentially don't modify vector as you iterating. And it's actually kind of dangerous, right? So you take in a pointer to an element and then you are pushing, which may cause reallocation, invalidating this pointer, right? So you can't just iterate and push simultaneously unless you stop using pointers. Who cares? That's a good question, honestly. That's a good question. Any language is memory safe if you don't give a shit anymore. It's like, yeah, I think it's from my latest tweet, so it's actually fine. My epic memes. Okay, I was about to close it. Yeah, so essentially concurrency is fearless in any language if you don't give a shit anymore. So yeah, any language is memory safe if you don't give a shit. So okay, we can actually do that if we stop using goddamn freaking pointers and start using indices. So let's actually iterate those motherfuckers by indices. So for usize I polls len, right? And instead of like you know, accessing poll, we're gonna do polls I. So essentially, if you push it, you're gonna just do another extra iteration, right? And I suppose we have to be a little bit careful. I think we should ignore all the polls that have their R events equal to 0. Right, so because if they're equal to 0, that means no events has happened to them. And if we push a new one, it by default has R events equal to 0. We can even explicitly put it in here. Right, just explicitly put it in here. So essentially what we want to do in here is just like polls I are events. If they are non-zero, only then we're trying to distinguish them and shy select that. Right. So then, okay, if it's a server socket, we do one thing. But otherwise, if it's not a server socket, we have to do one of the events, right? So since it's an echo server, we can either read the message or write the message that we received from the client. So since we're going to be reading and writing data, we need to allocate a buffer for that specific data. And since we're actually maintaining several connections, so that means we need to have a buffer per connection. So what I'm thinking is that we need to have some sort of a client structure, right? So some sort of a client structure, which is going to have, you know, the buffer, right? So which is going to be, you know, it's kind of similar, right? So it's kind of similar to the thing that we were implementing before, right? So the logic is basically the same. So this is the buffer. This is the buffer. And I suppose, right, we need to maybe do some sort of a hash map that maps the client to, not even a client, but socket to a client, because at this point we only know the socket, right? We only know the socket. We need to somehow distinguish, right? So know what is the association between the socket and the buffer it corresponds to. So to do that, we can have a hash map, right? So let's go ahead and do that. So I think somewhere in the collections, in the conniptions, we have a hash map. So there you go. So here's the hash map. Look at it. Look at that, chat. Look at that. So let's do a hash map. And so on top of polls and a list of polls, we can have a hash map, which maps, I suppose this is the native socket, right? So we map in native socket to the client, right? So that's essentially what we're doing. And this is clients. So that means as we push a new poll, by the way, just a second. Everything's fine. So the fan is working very loudly. I'm a little bit worried what the fuck is going on. Ah, no, everything's fine. Okay. Everything's fine so far. So, right, on top of just adding these things, we also need to create a new client. Right, so we need to create a new client. So we need to do something like clients, insert, or maybe I think it's success. Right, so we're setting client sock, and we need to set it to like a default client. I wonder if we can do something like that. Right, so because I don't really need to set anything in here. Right, so here I'm gonna just do unreachable, and I'm gonna just do a to-do saying that it's not implemented yet. Let's try to compile this entire thing, right? So because I don't want to go in code for too long without compiling anything. So no module std collection, or is it? So this isn't like about something about hash map. So hash map. Oh, okay. So the module map located in the file hash map. Anyways, so, but maybe that makes sense, right? So this one is map, like so, and let's fucking go. Oh yeah, this code will never be executed. Look at that. So since it's an infinite loop, we have a little bit of control flow analysis and stuff like that. So we never actually have to do anything like that. And does it compile? So it seems to be compiling. Everything is working. Everything is working. Okay, cool. So now, right, what we can do. We are in a client. We hit the client socket. So, and essentially now we need to know what happened. You see, the client can be in two separate states. When it's waiting for input from the client, and when it's trying to write the output. The question is how we're going to be distinguishing those things. We can create additional flag in here. Yeah, we can create an additional flag in here. So essentially, but I mean, I think it would be easier to actually keep track of that state through the events, right? Because if events is set to read, that means you're in a waiting for input state. Then when you're going to be in a state of submitting the output back, we can change it to write, and it will simultaneously serve as the indication for the kernel that we're waiting for those events, as for us that we're in a certain state. So I think that's a pretty good idea. So essentially, this is a client thingy, and so let's actually switch upon a different states. So this is going to be, we need to get, you know, the socket. So it should be really easy. So you do pulse I event, and it's going to be a switch actually. So, and in here you can be in case net subscribe read, right, and then net subscribe write. So if it's something else, let's actually mark it as unreachable, right? So unsupported state, state of the client. So here's the break, and here's another break. So if you are in a read, what you have to do, you have to try to read from the socket, right? So we need to first of all get the socket, but I think we already have the socket, right? So it's basically I sock, but we need the client. So essentially what we have to do, we have to do clients get. And if I remember correctly, you have to get it like by the reference or something like that. So there was a get, yeah, there we go. So you have to get it by the reference. So we get by the reference, and it may fail, right? But since we know that it will be always available, I think it makes sense to assert that and actually unwrap this entire thing, right? So this should give us the pointer to the client, right? So here is the client, like this. So that means if we're in a read state, what we can try to do now, we can take the pulse I sock and we can try to read it. And we need to try to read it as the entire buffer, right? Let's actually try to read the entire buffer. So we also need to keep track how much we read. So we probably should keep track of that in the client itself, right? So because it's going to be useful on the next iteration when we do the write. Right, so this is going to be this. And it may fail, by the way. But here's an interesting thing. Since we received an event read on that specific socket, we know that this read operation is going to be successful because this is exactly what we subscribed for. This is exactly what we subscribe for, so we can basically unwrap it right away. And if it's not would block, well, I mean, it's a legit error that we want to report anyway, right? It's a legit error that we want to report anyway. So here is the going to be client N, right? And after we read a chunk of buffer, right? Chunk of buffer, we want to send it back to the connected client. So that means we need to switch to our state. So we go and set pulse I event subscribe write. So that means on the next iteration, it's going to be waiting to write events instead of read events. And when write events occur, when the socket is ready for writing, here in this switch case, we're going to actually go to the write branch and we're going to perform the write in here, right? But a little bit later. So that's basically how it works. It's a state machine. It's a two-state machine. And this is one of the reasons why implementing futures library is because right now, this particular state machine is super simple. But as it becomes more complex, you really need to really think about this entire state machine. And it's better to have some sort of a simple framework that allows you to sort of construct these state machines for you, like futures library, right? If that makes any sense. So yeah, and it's a very simple thing. It's a very simple thing, right? So we go to write. And but here is an interesting thing as well. If client N actually return you 0, that means the socket is kind of closed, right? So that means we need to remove it. Yeah. So to do socket closed. So the socket has been closed. And something like that can happen on write as well. So what I'm thinking is that maybe it makes sense to kind of factor this entire thing out to somewhere, to some sort of maybe client operation. Right, let me think. Something like, it's going to return Boolean indicating whether it's succeeded or not. Right, or whether it's time to close or not. Right, so, and we're gonna do client poll, maybe, yeah, let's call it poll. And it's gonna accept self, and it's going to accept the pointer to the poll that it's operating with. Right, I'm gonna move this entire logic in there, like this. We're gonna move this entire logic in there. So here we have to replace polls I with poll like this. And essentially, if we read a thing that is equal to 0, that means the socket is closed, and we're going to return false in this specific case, right? So we return false. So I think I want to indent this thing like that. There we go. And otherwise, when we succeeded, we just return true. Right, so we switch to write and we return true. Okay, did I miss anything? I don't think I missed anything anywhere. But anyway, so now we are in a write state, right? And now we need to keep track of how much we actually written. So let's actually introduce like a second pointer in here that is going to keep track of how much we've written. So essentially, if you think about the buffer like this, right, so then you filled up a certain amount up until this point, and you have n, right, so you may want to also introduce I that keeps track of how much you've written up until you hit n, right, something like that. So that's basically the idea in here. So, and after we switch to write, I suppose one of the things we can do, we can set it to 0, self I 0. Okay, so I'm gonna do poll sock write, and I want to write exactly client buffer, but it's gonna be, it's actually self I self n, right? So we're writing that. I'm a little bit worried that the fan is going off like really crazy. Even though, surprisingly, I'm not doing anything, right? So at least htop doesn't show anything. Right, so and in here we just do that, and here we're gonna get a thing. Do I want to unwrap it right away? I suppose I do want to unwrap it right away. So it's gonna be something like that. If whatever we've written is actually 0, that means the socket is closed, so it's actually returned false in this specific case. Okay, so after that, we need to advance this I pointer, and we need to decrease how much we have in the buffer, right? So that's basically what we have in here. And then we just return true. But it also depends, right? So if, for example, self n became equal to 0, that means we finished writing everything, and we need to switch back to the read states because we want to do that in a loop, right? We want to do that in a loop. So we want to set the poll, to read, like so. Right. So if we finished writing the entire buffer, we just switch to the read state and we repeat this entire process, right? We repeat this entire process. So now here, we moved all of that stuff outside, right? So we only work with the client. So with the client, what I want to do, I want to just poll this entire thing on the polls in here, right? So I just do it like that, and then I take a pointer to that, and there we go. So if it succeeded, I don't do anything. So the only thing I care about is when it didn't succeed, right? When it didn't succeed, that means that specific client is closed, right? That specific client is closed. Obviously, one thing we need to do, we need to remove the client from the hash map, right? So we need to do something like remove, and we're just removing the socket. But on top of that, chat, we need to also remove the polls, but the polls is a dynamic array. And it's not only a dynamic array, it's a freaking dynamic array that we are currently fucking iterating. Okay, if pushing stuff into the dynamic array that we're currently iterating is easy, right, it is easy, but removing stuff from the array that you're iterating, that's already something interesting. So how can we even fucking do that? Right, so let me see. So we have some sort of like A, B, C, D, E, and we have an I, right? Iterator I. It's looking at C. We want to remove C and continue iterating. Look at that. As soon as we remove it and just like shift it back, we're already pointing to the next element. So that means that on this specific iteration, we should not advance I. So if we are removing the element, we should not advance I. And we always advance an I in here, which is kind of a pain in the ass, right? Which is kind of a pain in the ass. So what I'm thinking is maybe we should actually advance on demand. Right, so in here, essentially, if we hit this branch, we definitely want to advance to the next one, so I'm going to just do plus in here. If we hit this specific branch, we probably don't want to do any of that stuff. Well, obviously, we want to also close the socket. I think that's mandatory. And then we want to actually remove at I in here. But we never advance this entire thing. We never advance this pointer. Otherwise, if the thing was successful, we do advance the I. Right, so this is the only place where we don't advance the I. So A++, right? So we're going to comment it out. Maybe, yeah, something like do not advance the I. So maybe it would make sense to actually put this thing in here. Okay. So now, I wonder if we actually don't really need client. Yeah, we don't really need client anywhere. So that means I can inline it like that, remove this thing, and then I can actually flatten this thing syntactically a little bit, just a tiny bit. Right, which is probably a bad idea because you kind of don't expect this condition to do side effects. But it does side effects. But anyway, right, so we have three situations in here, three branches. In this one we advance, in this one we advance, but in this one we do not advance, right? And there's another situation is when the current poll that we're iterating doesn't have any events. In that case, we advance anyway, right? So something like that, we always advance. Or we could always advance, but maybe like just put I++ at the end and put continue in here. That's another sort of thing we can do. Right, so always do that. But it's kind of difficult to sort of keep track of the control. Yeah, like I don't like that. It's probably going to work, right? So just like never do ++ anywhere. And on this one, just do not advance I. Right, this one is probably easy, but modifying this one is kind of difficult, but I don't know. It's kind of difficult to tell. But it's much simpler, right? So we always advance. And this one is just continue. So, yeah, I don't know. Right, and I guess that's it. That is basically it. So we could actually do minus, right? So one of the things we could do minus, but I find it kind of finicky. So anyways, I guess that's it. So let's actually go ahead and maybe try to compile this entire thing. So let me see, 66. So we have to put parentheses in here, and then we have to put semicolon in here. Right, so then 30, we're going to put this thing in here, and 16, this is actually poll. There is no field or method event because it's S. And another one, 20, S. And another 120. It's actually right, it has to be part of the net. Alright, so then this is the client. Every time we refer to client, we just do self. Right, so this is something like that. And what else do we have in here? So 18. Poll, it's a socket. It's not a socket. There is no read on int. So you can only do read on full TCP socket, but we don't store it anywhere. We can store, like, okay, so we have two-tier socket. We have a TCP socket. Where is it? And internal native socket. I only store native socket. I think it makes sense to maybe keep track of the TCP socket in here. Well, let's actually do it. So, and when I do this one, I can do socket. And this is just a client, like so, right? And when I'm closing this stuff in here, yeah, I guess that should be fine. So this is a poll socket. This one has to be self socket read, and there is no poll socket 25, and this one is actually self socket. What else? And 29, this is net socket. It's events as well. 69. And here we get reference. So what exactly you don't like? This is just a socket. And then 70, this is just a socket. 71. I don't like how learner choose the inconsistent naming between sock and socket. Why the heck did you do that? Can anybody explain to me? Now, like, I can't choose, like, which one is it? Is it sock or socket? Fuck's sake. Anyway, so, by the way, people quite often ask me, like, why don't you just use LSP that always shows you these freaking errors, like, every time you type in and stuff like that? And I think I already explained that multiple times. People just don't listen to me. But I keep explaining that over and over again, is that when I'm typing out the logic, I don't want to be distracted from just laying down my logic because I'm in a flow state. If there is a constant blinking, like, you know, pop-up-in shit that is like, you know, like a Christmas tree in front of you, it's kind of difficult to focus on what you want to write. Right. So because like the modern text editors and they just frantically just moving around things and just highlighting, look, bro, you forgot the semicolon. Just shut the fuck up. Shut the fuck up, please. Right, let me write my logic. I have a very specific idea in my head. Let me write my logic first. It may contain errors, it's fine. I understand that people are insanely afraid of making compilation mistakes for whatever fucking reason. They have no penalty. Probably because of our stupid educational system where a professor will literally slap you in the face for compilation error or something like that. I don't fucking know what kind of trauma they have. Right. So don't give a fuck about errors. Finish your thoughts. And then on a separate step, okay, let's go fix up all of the compilation errors. Because when there is some sort of a LSP that right in front of your face constantly reminding you about semicolons, bro, I'm thinking about state machine. Shut the fuck up with semicolons. Spend 3 hours debugging and it was a single missing semicolon. Like you know what I'm talking about? Like I'm thinking about complex high-level structure, state machine, control flow, high-level architecture, and then you get knocked out of your thoughts with, bro, you forgot the semicolon. That's why you don't use this LSPs. You see what I'm talking about? This makes sense though, right? Because like when you've done that like long enough, it's actually kind of obvious, right? It's actually kind of obvious. But anyway, right? So just like I'm thinking about high-level things. And I don't care about these like minor syntactical mistakes. Who fucking cares? Then, when I'm done with my logic, okay, let's actually clean things up. Let's actually clean things up. Anyways, let's continue. So this thing seems to be working. I want to actually maybe print some information every time something happens. For example, somebody connects. I want to say something like connected, right? So we can actually see shit. Right, there we go. So connected. And when somebody disconnects, we also want to print disconnected. Disconnected. Maybe we also want to know how many of the clients we have in here. So let's actually print the amount of clients. So it's clients length. And when we are disconnected, right, so client's length as well. So when we write something or read something, we can also print some shots. So IO print fn read, and it's going to self n, and this one is going to be wrote n. All right, so let's try to build, and that seems to be working. Let's try to run it. Let's also write something meaningful. Something like, as soon as I listen, yeah, let's actually print something like print fn listening as d host and port. Like that. So okay, listening 69 as 69. Okay, so let's try to connect to this motherfucker. Tell net localhost 6969 connected 1. All right, can I connect the second client? Okay, what about htop? Well, apart from the obvious OBS, right? So we have 25%, but this is OBS. Nothing is really spinning. Nothing is really spinning. So now I can close this entire thing, and it's disconnected, and I can close this entire thing. Right, so this thing using a single thread, and it is not spinning anymore like that previous version. There we go. Yeah, as you can see, it is spinning. It is currently spinning right now. It's pretty cool. Are you happy now? Are you happy now? Yes, I know how to do asynchronous like networking properly. I wasn't doing it because I was busy designing API. Code is unfinished. Code is unfinished. It's not enough. Okay, I see. Now, okay. So now we understand. Now we understand how use this entire API. I think we need to start integrating that into the features library, right? So I'm thinking how we can even integrate it into a features library, right? So because features library kind of designed to be polled constantly, right? So you understand how to do asynchronous chat and stuff like that, but how do you fit all of that into the features library? That is very interesting. So, and I think we can't really integrate it the same way as efficiently as we did without the features, but I have an interesting idea. So look, when you make a feature, right? So when you're designing a feature, effectively what you're doing, you're building up an AST, right? For example, in here, so we have two features that we execute simultaneously, right? So we can do something like C3C run example, right? And you have two sort of like threads, not really like threads, running simultaneously. So I can comment out this one, like so, just a second. Comment out this one. So this is the first thread. Then I can comment out this one. This is the second thread. And if I do them simultaneously, this is two threads, but the application is actually single-threaded. Because what effectively features do, you define a small AST of a simple language that allows you to do these steps and stop executing, right? So you have two ASTs, and then you have an interpreter down below that runs those features and sort of schedules them manually. That's basically the idea. So features is essentially like a small script that you write in AST, and then you have an interpreter for this AST that schedules it depending on what you need, right? Depending on your needs, like it will schedule it differently, right? And in this specific case, we just like always poll them. But sometimes we actually don't want poll certain features because they are waiting on certain events to happen. How can we do that? How can we do that? That's a very interesting question. So if we take a look at the interface of the future, So it has a poll, right? And recently I introduced like a structure result, and it's a result of a single poll of the future, right? It's a result of a single poll of the future. So, and essentially what it tells you whether the future is finished or not. And if it's finished, it basically returns a value that it's finished with. So essentially, future usually knows when it's waiting for a certain event. I think what we need to do in here, and this is just like my idea that I want to try. I don't know if the futures library do it this way, maybe they do it differently, but I want to try to do it this way. Essentially introduce a second status to the result. Result can be right now in two states, right? It's pending, right? So we haven't finished the future, and finish and done, basically finished. Let's introduce sleeping, right? So essentially, if we go into the echo server that is, spinning and, using futures, here is the operation, here's the future that is responsible for it, right? So what if, when we try to read and we encounter would block, instead of returning pending, we would return something like sleeping, and we would specify, okay, I'm sleeping until this socket returns read. So essentially, and as soon as I encountered would block, I say, okay, don't even fucking poll me until this event happens. And it basically puts it in the back burner, right? And then in the next iteration, it performs the operating system poll. And if that event happens, it wakes up that future and starts polling it again. How about that? Right, so doing poll API is okay, but how do you feed that poll API into the futures API? This is my idea that I came up with. Right, so essentially you have a third status of the poll, which is sleeping. Future, usually when it hits a would block, it knows that it needs to wait for that event. Okay, right, so let's actually tell the scheduler, the runner, wake me up when that thing happens. And the scheduler would probably have some sort of a hash map, that just maps a certain socket, a certain event, and a future that is sleeping currently waiting for this entire thing. So that's something how C# task status works. Okay, that's actually pretty cool. I haven't looked into how other libraries do that. I wanted to come up with my own solution to that. I think the way I vaguely remember a long time ago that Rust futures, they also accept a pointer to the task runner in here, and you kind of tell the runner to make me sleep by calling one of the methods or something like that, but I don't quite remember. Right, so, and essentially it's not as perfect as our implementation in here, right, because it is so perfect that we can just unwrap reads and writes because we know they will never fail. Right, so in here, as you can see, we just unwrap them. They are non-blocking, but we're unwrapping them anyway because we know that they will never fail with would block, because it guarantees that we receive that event. Right. In here, it's kind of more difficult. Right, so I think the sockets would hit at least one would block, and that one would block is an indication, okay, I need to sleep for the event a little bit. Right, so it's not as perfect as it could have been, but I think it's a fair price for having the future API. So something like that. At least you don't spin on would block. You hit it once and then you go to sleep. All right, so that's basically the plan. I haven't tried to implement it yet, so I think I need to make a small break. Right, I need to refill my cup of tea, and then we're gonna dive right into it. How YouTuber says that, I don't know. Let's make some break. We are back. So let's go ahead and just introduce the third state for the result of the future. So let's see how we can do that. So since we had only two states, I basically denoted them with just a Boolean. I suppose the time has come to introduce something like, enumeration. Result state, or maybe just state. I think that would be better. So we're going to have something like done, or maybe pending, then done, and sleeping. Right. I'm not sure in which order do I want to do that. Let's actually make done the first one, then pending, then sleeping. So in here, instead of finished, we're going to do something like, oh, since it was called finished, for the consistency, I think I'm going to call it also finished. Yeah. Finished, pending, sleeping. Right, so state. And that kind of naturally turns into tagged union, isn't it? I think it is a tagged union, essentially. And when I'm sleeping, through the value of any, I can actually convey information about what event, like why I'm sleeping, right? And since it's any, I can use whatever value, and it's going to depend on the scheduler, right? Scheduler is going to expect a certain value in there dynamically. So we're essentially programming a toy scripting language in here. It's one of the cool things about any that I really like is that you have like a statically typed serious language, and then at any point, nah, fuck that, I want to program in JavaScript, and you literally start programming in JavaScript, and it doesn't add that much of the runtime overhead. It's just like basically a thick pointer, your mom pointer, right? So it's the address plus the tag, right? The your mom pointer, because it's thick, it has additional extra information. So yeah, so we modified the signatures and stuff like that. So we might as well, yeah, this one is interesting. So we have these extra macros that helping us to do things. So the macro sleeping, any value, we can also assign it to null. And in here, I suppose, since it's state, this one is going to be finished. this one is going to be state pending, and this one is going to be epping, peeping, sleeping. There we go. Additional comma. Right, so let's do C3 build, C3 foot. I didn't want to put the extension in here. I actually wanted to put echo in here, finally. So let's go through the compilation errors, right? So the compilation error has happened at here, so it's 30. Okay, all right, so foot sleeping, right. So sleeping has to return some sort of a value. What I'm thinking is that not in a library, but in the application where we're doing, I want to keep the library kind of like environment agnostic, right? So I don't want it to be purely about networking. So I think the library should not know the specific events that you can sleep on. It should be up to the application to define those types and to then define a scheduler and stuff like that, right? I think scheduling and exact interpretation of the futures and their results, it's up to the user of the library, right? So the library, the core of the library is sort of like a very much like agnostic to the problems that you're solving. But we may provide additional libraries on top of C3 foot that add supporting for networking, for some other things, right? Is that how Tokyo came to be, and that's why it has a lot of components like that, because it's basically that? Did I just reinvent Tokyo? For fuck, anyway, let's not think about that. Okay, so let's actually Tokyo for C3. Kokyo. It I just bit my tongue because of that. So how about Kokyo? Because it's a Tokyo for C3. What a banger name! Yeah, we should call it Kokyo. Kokyo. Anyways. So what I was doing, yeah. So we need to introduce something. So let's introduce a structure. Sleep until, right. Maybe socket wait. We accept native socket, right? So this is socket. And we accept like events, right? And it's going to be those subscribe events and whatnot. So where is the struct poll? Yeah, we can actually do poll subscribes, right? Poll subscribes, and it's just events. I think that's a good one, right? So native socket poll subscribes, and then you just add that information to your polls array. Right, and then you just like wake up this particular socket when it happens. So and essentially, since the result can only accept any socket wait, has to be a pointer, right? So we can do something like this, obviously, right? And we can even assign client sock like that. So that's the native socket, and we can say, okay, so net poll, yeah. What was that? Poll event subscribe. Hit like and subscribe, chat, right now. We can do something like that, but it's not going to work because any has to be a pointer. We can even try to compile that just to see how miserably it will fail. So this is TCP socket. Okay, so we have to do sock in here to make it as a native socket. Yeah, so you cannot convert pointers to any. So because of that, I suppose we can move that to heap. Right, at least for now. The memory management in this library is all over the place because, again, that's not the current point of the session. Just like with spinning in the previous session. Right, yes, I'm making shortcuts. I'm doing that intentionally because the current focus on something else. Calm down, okay? So no need to tell me that my code is unfinished. I already know that. I'm kind of working on that. Anyways, right, so locating a dynamic memory. And I suppose, I think it's going to be up to the scheduler who receives this sleep event to then deallocate this thing. Right, so we're allocating and deallocating small objects. But again, right now, I really don't want to care. Maybe in the future, we can just like have a pool of these objects, right? So some sort of a pool allocator, so to make it a little bit faster or whatnot, right? It doesn't really matter. So that's what we're doing. And that's how we're going to be sleeping on those things, right? So instead of pending, we're just sleeping. What's interesting is that in here, we don't even pend anymore, right? We don't even pend anymore, which is rather interesting. Right, but for write, we're going to be pending at least once, right? So in here, obviously, when we hit would block, we have to return sleep, and we have to tell what we're waiting for. There we go. So we are pending for the write. But write is different from read. Reading, we are reading thing once. Whatever we received, we switch in the state nonetheless. But when we are writing, we need to write everything. And because of that, if we didn't finish writing, we try again. And in this specific case, we can be pending, but not sleeping yet. So we try to write thing. Right, then we're gonna go on the next iteration, try to write again, we hit would block, and then we're gonna sleep until write occurs, right? That's gonna be basically the idea. So would block. So another interesting thing in here is the accept future, right? So we have a special feature for the server that does accepts. It can also block. Right, it can also block. And in that case, we can just wait for the read, right? Because as we already explored, accept wakes up when there is a read operation, right? So because accepting a connection is a read operation. So let's actually go and just copy paste that stuff from here. Let's just copy paste it from here. And now when an accept happens, we go into sleep. Otherwise we go nani. It's really funny. Nani is an error, right? So this thing is an optional, right? So we identify it as an error, and if it's not would block, we just do nani, and we unwrap it essentially. Yep. So let's go through the rest of the compilation errors. Yeah, what did you want? So here what I supposed to do actually, I supposed to do server sock and sock. There we go. Okay, so now we have the situations when we're trying to access the fields that don't exist anymore. Look at that. This one is interesting. Right, so we try to poll the client future, right, and we have the status now, right? So instead of if, we have to do switch case on these things. And obviously here we have one case, so this is one case, and here is another case, and the question is, what are those cases? So this one is when it's successful, right? So I suppose that's what it is. This one, it's when the future is successful or when it's pending, right? While we're pending, we keep carrying the clients to the next iterations. When the future is finished, we disconnect the entire thing and remove the client and stuff like that. That's what we're doing here. But now we introduced sleeping. And what do we even do in that specific case? And what's funny is that we also have to do that for this thing, right? So for the server future. So this one is sort of like unreachable, like to do sleeping. Sleeping is not implemented yet. So we can then close this entire stuff. Maybe I should have not done it like that. Yeah, there we go. So client's clear and stuff like that. So that's what we have to do in here. So obviously this schedule is not fit for what we're trying to use it for, right? So it should be just an array of futures. Like my sleeping schedule, also not yet implemented. Too real, man. Caffeine after 6. That's what I do. Okay, so let's try to compile this entire thing. Right, and let's go through the rest of the compilation errors. Status, is it not status? I think it's state, actually. Yeah, I called it state. I'm a dummy dum-dum. 117, it says state. Oh, right. So 84, that's another, oh, this one is interesting. Oh, it's already inside of the library. We are referring to the states inside of the library. That is very cool. Okay, I thought we don't refer to them. And it's on the line 84, right? So when something is finished. Okay, so if some of the futures is sleeping, ooh, this one is interesting. When it is sleeping currently, we have to propagate that sleeping result. Ha! That is very cool. So essentially, we take the state, and if the state is finished, only then we trigger the next future. So this is the then future. Then future has left future, and then the right future, which executed when the left one is finished. Right, and the right one is constructed through a then function. So essentially, when the left one is not finished, we have to keep propagating its result status to like upwards to the color of the poll. So we have to just like return result. But when it's finished, we're doing a different thing in here. But that also means that here we have to say pending. Yeah. Or interestingly even, we can try to right away poll the right feature. Huh. Or maybe it's not a great idea, honestly. Because we already performed one step on the left future, so we want to perform poll for the right one on the next iteration. So I suppose the easiest thing to do in here is to return pending. Right, so because it's not finished, because we have the other one. And in here is going to be result. Okay, so I'm glad that the compiler told me that I need to modify this thing. So Arcton, thank you so much for Twitch Prime and the message. A future investment. Yeah, that's what we're doing. So it's a future investment. Okay, so we have a future forever, the one that is executed forever. Okay, so when we have a state, so if it's finished, it's that. If it's state not finished, no, it's the other way. If it's finished, state equal finished, we just return that, and we have to return pending. We have to return pending because we recreated it. But if it's pending or finished, we have to return result. Okay, so that makes sense. Because it might be not finished, but it could be sleeping. And we need to propagate and tell the scheduler that we are sleeping. Right. So we need to tell the scheduler that we're sleeping. I watch your videos on YouTube, just came to say that you are amazing. Thank you. Thank you. I'm really glad that people from YouTube actually go to Twitch and try to engage in the chat. Cheers. Cheers for you. Okay, so let me rebuild the whole thing. Okay, seems to be working. I hope I didn't make any mistakes in here. And I suppose the sort of the baseground is ready, right? So our futures can already tell the scheduler that they want to sleep, that they're EP futures, but we can't put them, we can't, you know, put them in the bed yet. I just had an idea. The data structure that is storing the futures that are sleeping should be called bed. Anyways, so because you take a future and you put it into bed. So starting the new year of right. Yeah, exactly. That's what we're doing. Dormitory. Maybe that's another good name, actually. Something like that. And here's the thing: our schedule, it actually separates clients and server, right? So you see, it separately polls the server future and then separately the client's future. So which is not particularly great. So I think what we have to do, we have to have a scheduler, like a, you know, scheduler structure, or maybe like a runner. And in here we're going to have like a structure that just stores the futures, right? So here are the futures that we are executing. And do we have to make a pointer? It's an interface. It doesn't even have to be a pointer. So, and interestingly, right now, let me see. We always associate the future with the state, right? So here is the state of the client future, and it also knows itself, right? Because I was using that in a scheduler, right? So I was iterating the states, and then I would grab their future and just poll it, but that future will be modifying its own state, right? So if you take this future and you try to poll it, it's going to be operating on this state, on itself. I don't think it's needed anymore, actually. I don't think it's needed, so we can do something like that. The clients need to know about their sockets, but they don't really need to know about their futures. I don't think so. It doesn't really make much sense. So you have client, you have server, right, and here's the runner, you have futures and everything. And here we just create a server future, but I feel like now what we have to do, so here's the runner, we're gonna just assign it like that. We have to do runner futures push, right? So we created the server future which accepts and stuff like that, and we just pushed it into the list of these futures, right? So we pushed it into the list of these futures. Interestingly, now within this entire thing, we also need to create new futures. Look, when accept is successful, we create a new client future, and we're pushing it into the clients list and stuff like that. So because of that, I feel like runner has to be a global variable. I think it has to be a global variable. I know global variables bad. I know spinning on a synchronous socket is bad. I know goto is bad. There is no need to tell me all of that. I went to university. I listened to my professor. I know all of that. You need to know the rules to be able to break them, right? So, but in these specific cases that we have several futures that can schedule more other futures, and you can't capture the runner that easily. So, and you're not going to have more than one runner per application anyway. Right. Goto is underrated, actually, ironically. So there is some algorithm that are easy to implement as Goto. Goto in Jai soon, possibly? Honestly, so wait. Jai doesn't have a Goto. Just a second. So let's go to the modules and grep. Okay. Oh, it's all in the C code. The old code used goto, which we don't support at this time. True. But I mean, on the other hand, the fact that he never needed goto means that maybe it's not that important anyway. I don't know. So as soon as, like, the only reason why I would use goto in C, for example, is that because I don't have a defer. Right, so that's the only use case for goto for me in C. Jai has defer. So there's no reason for me, at least, to use gotos in Jai. But I mean, maybe there are some cases apart from that where goto is useful. But anyways. So here's the runner, and when we're doing this kind of thing, what we have to do like a runner futures, and you just push this entire thing, right? So and that's the future we push, and so we also do server clients and everything. Does server even need its clients? I'm not even sure. So we were needing it because so that's the equivalent of scheduling that future. All right, so we kind of like separating the states of the futures from the futures themselves, which is maybe a good thing, honestly, because this is something that was bothering me for some time, right? So because so futures and the states of the futures are kind of the same thing. So I removed this, swapping client lists and stuff like that. So we don't do them anymore. We actually don't do them anymore. So the client disconnect, I feel like it should also do something. So, okay. So I'm gonna sort of comment this thing out, and we're gonna have a completely different schedule in here. So I'm going to just iterate the futures of the runner. Just iterating the futures of the runner. So future runner futures. I don't even have to take them by pointer. So at some point I will probably have to iterate them by an index, but whatever. So future poll, right. And if it fails, we should allow it to fail, right? So we can maybe handle the errors a little bit later. So we poll the future, we take the state, and that's basically what we're doing in here. So that's basically what we're doing. So if it is pending, we just keep doing what we're doing, right? So we're just like ignoring the fact that it is pending, so that means it's going to be on the next iteration anyway. So if it's sleeping, it's unreachable for now, right? So let's actually even take this thing. Let's actually take this thing and put it like this. If it's finished, we have to evict that future out of the schedule. Is that a term that is used in schedule, like evicting? So because they're like tasks, right? So it has to be like finished and removed from the list and stuff like that. I think it has to be done. Abort, yeah, abort the future. But definitely what has to happen is that future has to be destroyed. That's for sure. Or maybe, by the way, we can employ a similar technique of two lists, right? So you can have a list of active futures, right? So this is basically active. So the ones that we are, you know, currently polling. And then we can have sleeping, but those are going to be sleeping on certain events. So because of that, I think it's not going to be like this structure, right? It has to be maybe a hash map that maps a native socket to a future, right? Because when event happens, we have to take that future and put it into the active, right? So these ones are sleeping, and the ones are basically next active. So essentially, yeah, there's like 3 buckets in here. So we pull in active futures. As we pull in them, right, if they're pending, we keep in them, maybe we're even adding them into the active list, so they just stay active. And then we're swapping them around. But maybe it's, I'm not sure how good of an idea that is, but yeah. So when it's sleeping, we're removing it from the list. We don't add it to the next, but we're adding it to sleeping. And when it's finished, we just destroy it and never do anything about it. I think that's a good way to do that. Right, if it is pending, runner next active, just push that future in there. Right. So when it's sleeping, we need to take the future, actually the result value, which means that we need to store the result somewhere, right? So it has to be result like that. So it's a result state. So here, what we have to do, we have to take the result value. And so far, the only sleeping value that we use is a socket weight, right? So this particular structure, it's a socket weight. So that means we have to perform the any cast of this thing to socket weight. And we get a socket weight pointer. So this is a single weight. And it describes what we have to do in here, right? So it describes, so that means we need to take a runner. So sleeping, I wanted to call it bed, didn't I? I think I wanted to call it bed, right? So we're putting them into the bed, right? So I set essentially weight socket, that future, and I don't add it to the next active. Just a second. Something in my kitchen just fell over. the fan in the basement. Don't worry about it. Excuse me. Yeah. Okay. So we just do that, and then we do that, and so on and so forth. All right. So, and after that, we should not forget to do the swap between the lists, right? So we do swap running active. So this is actually active, right? So that's what it is. Swap active, and then runner next active. But we should also not forget to clear the whole thing in here. Clear the whole thing. Okay, that's pretty interesting. Now let me try to, yeah, so we can actually remove this entire thing. That's pretty cool. As we put all of these things into sleep, what we have to do, we have to also maintain the list of polls. That's what we have to do. So let's actually do list poll. So this is polls. And essentially, when we put this thing into sleep, I just do runner polls, and I just push a new poll. That poll has a socket, which is the wait socket. Then it has events, which is a wait events. And our events is going to be 0, right? So because this is what the operating system is supposed to return to us. So we performed like a single poll on all of the futures, and we essentially came to a conclusion that, right, so these ones are going to be the next active, and so on and so forth. Some of them are going to be already destroyed, and some of them went to sleep, right? So that's basically what happened. I suppose after that single iteration, what we have to do a poll, right? But it also very much depends on whether we have any more active futures or not. Because listen, we can have some of the active futures still running and some of them that are sleeping. That's what we have right now. We want to poll with the infinite timeout only when there's no more active futures and there's only sleeping ones. Because of that, depending on how full runner active is, we're going to be calling poll with different timeout, right? So if there's still some active futures, we want to run a poll with the timeout 0. So it just checks for the events, and then continues for the rest of the active futures, right? And if there is no active, there is no point in even running anything because you're going to fall back into spinning again. So just go infinite timeout. Right, so in here, what we have to do, so after we did this single iteration and we figured out what's going to be the next active, who's still active, we need to check its length, right? So if the length is essentially 0, only then we sleep with the infinite timeout. So let me steal some code that we did in poll try at the beginning of the stream. So where is the poll? So here's the function. So this is what we want to do in here. So if it's equal to 0, it's going to be -1, right? If it fails, it fails. So, but we have to do the following thing in here. So we have to do result. So we have to do the, not result, but the runner. So this is the runner, and this is the runner. So this is the infinite thing. If it is not empty, I suppose we literally have to do the same thing, but with a timeout equal to 0. So it just checks for any more events, right, for more events, and then goes back into polling these things, right, because none of them like fell into sleep or anything. So we might as well maybe compress some of this stuff, right, so we can put this thing like that, right, and then just like merge that stuff together. Or we can even, yeah, we can actually define a timeout like this. So this is going to be timeout, right, and if it's equal to 0, right, if it's equal to 0, it is going to be a -1. Otherwise, it's cint 0, right. So because of that, we can just get rid of this nasty if else, and just keep it like this. Right, so we put the condition in here. It's pretty cool. It's pretty cool. So after that, some of the futures have woken up, right? Woke future. It's we need to search for woke futures. Right, so I'm gonna do for each. So this is gonna be, yeah, it's gonna be similar algorithm that we're doing here, right? So we're gonna be iterating through polls, right? And then if one of them woken up, we're gonna be moving them into active ones, right? So then on the next iteration, we can do something with them. So for, do we have, okay, so it's fine. I was thinking maybe we've already taken the variable I. Ooh, I just realized that I did something nasty. I'm supposed to actually keep this code outside of the inner loop. I'm glad that I noticed that a little bit earlier. Futures becoming woke, yeah. What the heck is question mark, exclamation mark, exclamation mark? It's basically unwrap with panic, like in Rust. That's what it is. Unwrap with panic. All right. So let me actually think. So this is going to be the iteration. It's a mad question. Yeah. Nani. So let's iterate the polls. Right. So this is going to be polls. It's going to be len, and I'll go. It's kind of a similar algorithm that we developed in here, actually. So we need to check for the polls that have our event of some sort, right? And futures. Literally my entire life in a single line of code. Anyways. If it's our events, what we have to do, we have to look up. So we have a socket, we have a socket, and we can look up the bed by the socket. So here's the bed, and we get by a reference. Well, it doesn't even have to be a reference because future is a reference itself. Right, so I just get the future from the bed. I'm gonna unwrap it because I'm sure that it exists in there. And I just push this thing into active. Can your Rust do that? Can your Rust do that? And I think so. But by the way, maybe the borrow checker of Rust became advanced lately. But as far as I know, this kind of shit is kind of difficult for Rust because you're kind of borrowing this thing as read. And then you're borrowing this thing as write, and you're pushing one thing into another. And usually borrow checker, remember being like tripping over this kind of stuff, but maybe they actually improved it. But this is like a this is a no-go for Rust, actually. It's kind of funny in my opinion. Still can't do that. Holy shit. Like, yeah, so for the longest time, borrow checker in Rust would actually disallow you to do a valid code for the sake of safety and stuff like that. But they've been trying to improve that and stuff like that. But this particular part, they still can't do that. They still can't do that. Like, I mean, you can always work around that by doing something like this. And then you can make a smug argument is that you have to do that anyway. You say Rust is forcing you to write more readable code. You see what I'm talking about, right? So that's usually basically the entire Rust argument, right? So you see some bullshit, the borrow checker. I mean, it's forcing you to write readable code. You uneducated, filthy pleb. Anyways, so we're gonna be writing, filthy, uneducated code instead. So, so we're taking this entire thing and we're pushing it into active. Do we need to do anything else? I feel like we also need to remove the polls. Similarly, how we remove them. That's what you have to do in C sometimes because of the okay. So because of the optimizations, yeah, all right. I agree that that's how you have to do it anyway. All right, you fucking won. What the fuck do you want from me? I'm gonna write it like that. So anyways, and because of that, I suppose we want to do something like this, right? So we push this new thing, but we also need to remove this stuff, right? So remove at I, right? And then we continue like this. Otherwise, if we, yeah, so woken up, the other one did not wake up. The other one did not wake up, so we just leave it as it is. Wait, I can't believe this is it. This is actually it. If I did everything correctly, this is basically the entirety of the algorithm. What the fuck? Wait, did I miss anything? Well, yeah, I missed one thing, right? So because I leak a little bit of memory, so one thing I want to do in here is free the weight, right? Because it was allocated on a heap by the future, and then we have to not forget to free it. But apart from that, I don't see any problem. We can even, like, specifically for the weights events, we can use reinvented. Okay, we can use a temporary allocator. Use allocator temp for socket weight allocations. Yeah, so basically allow the futures to shed diarrhea beam of socket weights within a single iteration, and then just clean up the diarrhea beam on each iteration at the end of each iteration. I think that's easier and that it's going to be faster. Right, so because they have to exist only until the scheduler actually processes it. As soon as it processes it, like if we don't care about it, it may die. Future destroy. Okay, let's try to compile this entire thing. Might as well even just do, I don't even know. Just in case, I'm gonna put else in here, plus plus. Yeah. So we take that. Let's go to the compilation errors. Build echo. Cool. 118. So future. It's a for each. So is it fine? So we don't modify active in here, right? So we only push into the next active. So that's totally fine in my opinion. That's totally fine. Oh, by the way, so I'm doing remove at, right? I'm doing remove at, which is O of n. I think I saw Andreas Kling some time ago suggesting an algorithm of removing element in the middle of array in O of 1. Do you guys know this algorithm? It only works if you don't care about the order of the elements. Right, so A, B, C, D, E, F. Imagine you have this array and you need to remove C and you don't care about the order. You swap around C and the last element and you just remove the last element. Swap and last. Maybe we should employ this thing in here. So Rust has that algorithm built in. Bro, it's literally 2 lines. You don't need a PhD to implement that yourself. Anyways. Like, the fact that Rust has that in a standard library is not an achievement. Just saying. If you don't care about it, won't just sequence backwards? I don't know. Anyways, so I guess that's it. So that seems to be working. That seems to be working. Hash maps. Yeah, we need to include map. Oh, by the way, server used to actually keep track of the clients because we use this client list as the schedules. We don't need that scheiße anymore. We don't need that scheiße. Okay, so I'm going through the compilation errors now. So we don't need that stuff anymore. Damn, that actually, this scheduler actually simplifies everything. I really like that. That thing simplifies everything. So 85 runner futures. It's actually active, right? So we just add it to the active. And 101. Yeah. So we are appending them to active ones. We might as well even do something cool. Right, so because active, not active, it's kind of an implementation details and shit. What if we introduce a method? Oh my god, it's gonna be so fucking crazy, I'm telling you. Scheduler. You provide the future, and it just schedules it. And the way it schedules that future is just adds it to active one, right? So it's gonna be self, active, push, future. There we go. So instead of doing push, what you do is basically schedule. Look at that. So you create a future with a poll function and then you schedule it in the runner. That's an orgasmic API. Holy fucking shit. Okay, and then you schedule that future. Look at that. Look at that. It's literally Tokyo, isn't it? I haven't tried Tokyo. I think I should try it at some point. Yeah. My rule is that I never try libraries until I try to implement them, right? So I'm gonna implement my version of Tokyo, only then, okay, I'm gonna look into your take of asynchronous features and shit. Right, so I'm first gonna come up with my take. Anyway, I'm sorry, I'm joking, obviously. We must rename this library to Kokyo. Right. I'm gonna schedule a stream where we're gonna look into Tokyo, right? We're gonna explore Tokyo. And if it's like Tokyo, we're gonna call this library Kokyo because it's C3, like, you know, instead of TC and stuff like that. Kokyo. All right, what else do we have in here? Anycast. It didn't like Anycast because, oh yeah, it may fail. 126. I'm gonna assert that because I'm certain that these things are gonna return that. What else do we have in here? 130. Events. It didn't like events because it's not called events. It's called event. But there's several of them. So that means I need to now modify all the places where I made that stupid fucking mistakes, man. Stupid fucking mistakes, man. I swear to God. Especially if you start copy-pasting them. Alright, so 145. And something I don't understand. So polls. Ah, yeah. It's a runner pulse. Runner pulse. Pulse. Fucking now I have to prefix them over and over again. Very freaking cool. Very freaking cool. There's another interesting thing is that if you end up essentially with no active futures and no sleeping futures, it's kind of like over. We can have something like runner done. Right. Runner is done when it has 0 active futures and 0 sleeping futures. I think that makes sense. So OS poll has cint instead of timeout arg. Really? It has a default thingy? Let's see. Let's see, chat. Let's see. OS POSIX. I mean, what? Anyways, I thought you said that it has timeout as a default value or something. But I mean, whatever. So runner done. And in here, we're gonna just do self active len equal to 0 and self bed len equal to 0. So there's nothing active and there's nobody in the bed, right? So maybe we should call this kitchen. So there's futures in the kitchen that are currently cooking, and there's futures in the bed that currently, holy fucking shit, okay. Kitchen. This is stupid. This is the dumbest shit I've ever come up with, but I like it. There's two spaces, two places, right? So the futures currently cooking in the kitchen and the futures that are sleeping in the bed. Base naming it. It makes sense. It's self-explanatory. Right. Kitchen and bed. Kitchen and bed. Let them cook indeed. So build echo. Chat, I'm stalling at this point. I'm literally stalling because I'm afraid to try that. Because that's basically it. That's the entirety of the algorithm. I didn't expect that it's going to be so fucking simple. Right, so I'm just afraid to try it. So let me actually do htop, and I'm going to look for echo. Right, so I'm going to be just like searching for echo. And let's just try to run this entire thing and see how it fails. It didn't fail. All right, so far we can take a look at some of this stuff, and I don't see red core looping. There's one bulging out a little bit, but this is OBS. I'm telling. Okay, you can clearly see that CPU is 0%. Right, you can clearly see that CPU is 0%. Okay, so the time has come to maybe try to telnet to this thing. Okay, the client is connected. So we can maybe bring this thing to here, and the future is not doing CPU 100%, and now I can try to send some data, and it's blocking. That's very cool. Right. So something went wrong, and I wonder why. So this one is a very interesting question. Oh, I think, so this is what the chatter was saying about mine. Okay. I see what you were saying. Well, I mean, whatever, the compiler would catch it, right? Who needs chat? You have a compiler, right? So it's just the borrow checker would have caught that. Yeah, I know, I already fixed it. If it compiles, it works, am I right? If it compiles, it works. Okay. Alrighty. So it seems to be working. I connect, client connected. The CPU is 0. Okay. Fuck! Okay. So something is still not working. Something is still not working. I wonder what exactly. So maybe we can log the futures that are currently sleepy peeping. So let me see. Socket wait. So I sync read, and I'm specifically looking for that socket for read. Okay, so that makes sense. Write. Okay, so that socket and write. That makes sense. Okay, so accept the server socket read, and that is in fact a read event. So we are doing everything correctly. And here we're always pending. So we did the connection, we did the connection, and we added this entire thing to the kitchen. Ooh. Yeah. This is nasty. This is nasty. You know why? Because when we schedule those mother flippers, right, when we schedule those mother flippers, we're adding them to the current kitchen that we're currently modifying. Right, so look at that. We are polling futures, and as we poll futures, they can actually push into the kitchen more. See what I mean? They can push more into the kitchen. So because of that, I feel like when you schedule a thing, you have to push into the next kitchen. Right, you have to actually push it into the next, so then it can be swapped out. Right, so at the end, when you swap out this thing, right, it's going to actually properly schedule them on the next iteration and stuff like that. Dirty kitchen, yeah. Maybe we should call it dirty kitchen. Damn. Wait a second. So it's this is dumb. So there's the main kitchen and there's a dirty kitchen. So, and I suppose here's the interesting thing. We start scheduling shit before we even started the main loop, which kind of implies that we have to do this one simple iteration like right before going into the loop so we can properly schedule out the server. Right. So I suppose this operation of swapping out the kitchens has to be the operation of the runner, right? Like sort of like swap buff. This is a double buffering, isn't it? So we're basically doing the double buffering. Okay. So anyways, let's try to rebuild this entire thing. Telnet. Holy shit! All right. So can I connect another one? Telnet. Boom. And look at that. Where is the Scheisse? 0% CPU. 0% CPU, asynchronous, single thread, 0% CPU, asynchronously handling several clients. Look at that. Everything is fucking working. I can even close them. They're closed automatically. Everything is fucking working. How about that? Are you happy now? Are you happy now? People have been, you know, hating me for, you know, you're spinning, you're doing it incorrectly. Now I did it correctly. Now I did it fucking correctly. So our asynchronous future thing, asynchronous future library is working exactly as intended. It's efficient, it's fast. We're gonna win over Tokyo. Who needs Tokyo? Who needs Tokyo when you have Kokyo? All right. So I think there is a little bit of a fucky wacky in here. Because, yeah, we did a fucky wacky because as I was refactoring, I removed the code that closes the sockets and deallocates the memory of the client and stuff like that. Happens. So let's quickly do that. But I mean, that's besides the point. The core idea is implemented correctly, more or less. Right, so the core idea is implemented correctly. Essentially, here is the client future, right? So it's a forever future that does a synchronous read and then performs a synchronous write, and it repeats. Then we take this forever future and we catch in an error inside of this thing. So we might as well, I feel like I need to inline this entire function because it doesn't, you know, serve any good. All right, there we go. So we catch in this entire thing. It doesn't even have to have a name, right? And if the error that was thrown outside of the forever is client closed, we're just declaring this future done. But one of the things we have to do in here, is free the client, because as you can see, we allocated that client in the dynamic memory. You have to free the client, but on top of freeing the client, we also have to take the client and its socket, and we have to close that socket. Well, to do it properly, we also have to drain the input buffer and stuff like that, and also shut down the ends and everything, right? We already did a stream on that, right? But I don't want to do it right now, right? So we can do that a little bit later, right? So close this socket properly with shutdown and shit. Snow godem with us. All right, so yeah, I think that's basically it. But the problem is, it's not going to compile. Look at that. So names of the what? 21 what? Names in the upper. Did I? So this is that, because I have to, yeah, I have to actually put an extra parenthesis. Okay, cool. We don't have an access to the client because C3 doesn't have closures. It literally doesn't have closures. So yeah, we don't have an access to this client thingy. I think the only way to do that is to actually pass it as an argument. So we need to go and extend the future and basically pass the client as a pointer in here. And then here we're going to have the argument, which then we'll have to cast to the client. We're casting it to the client, and only then we'll be able to use it properly. I think that's what we have to do in here. So that means we need to massage the API a little bit to do that properly. On top of this kind of stuff, I also want to say that the client was disconnected. Disconnected. There we go. So the client was disconnected. Let's try to compile this entire thing. Okay. So as you can see, future catch fn is not correct. Right. So because it doesn't accept this argument. And if we're going to be passing this argument, we have to retain that argument within the future catch in here. Right, so we have to retain it within the future catch. So, and as we're constructing this future catch, right, we have to put this argument in here. But we can actually assign null as the default thing in here. Right, and then we're going to be actually putting it in here. So it has to be arg. So now every time we call catch fn, we have to pass that argument in here. Yeah, so that's basically how we're going to go about that. I'm sure if it's a good idea, that's something. Excuse, I think argument, do we, yeah, it's the other way around. So first comes that and then excuse. All right, so that seems to be working now. Now what I can do is telnet, boom, then close, and it's disconnected it. Right, it did connect it, then disconnected. All right, so let's do telnet, telnet. So we have 3 of these things: hello, foo, bar. Let's take a look at the htop. Do we have htop? I already closed htop. Echo. All right. Single thread, CPU 0. All right. That's pretty cool. I'm actually super happy about that. So let's close this thing. So this one is still working. Okay, let's close this one. This one is still working. All right. All right. I'm actually super proud of myself. Yeah, I knew how to do asynchronous API, but then I felt like I'm gonna have a trouble marrying together the asynchronous stuff and the futures API that I came up with. But the way I actually resolved it actually makes a lot of sense. It's not perfect in the sense that futures still hit would block from time to time, but they use that would block as an indication that they want to sleep on that specific event, right? And then they can tell the scheduler like how exactly they want to sleep, and the scheduler can actually like perform that. And the scheduler that does the sleeping is super simple. It's actually literally 3 structures, right? So struct runner, right? So it's just a list of futures, right? Then a list of dirty futures for the next iteration, and a hash map that maps the socket that we're waiting on to the future, right? And also, okay, so the forced operation is only to interface with the API. By the way, so we have a list of polls that we pass to the kernel, so the kernel knows what we're waiting for. And we have to maintain this list ourselves. As far as I know, the next iteration of this API called epoll actually maintains that list in the kernel, right? So you create epoll, and then you don't create a list in your memory, right? So what you do is you do something like epoll, I think add, or I think CTL, yeah, so you do that through CTL. CTL takes the file descriptor that was created by epoll, and then it takes operation. And operation is add a new file descriptor, modify file descriptor, delete file descriptor. So essentially that list of polls that we maintain ourselves in our user space, when you use epoll, it's maintained in the kernel. So yeah, you can actually simplify this API if you use epoll, right? So you wouldn't need to maintain this list yourself. Maybe I should do that actually. I never tried epoll though, so I feel like I'm a risk to go into the rabbit hole, so probably not going to do that. But essentially, if you use epoll, you don't even have to do this, like, you know, list management. You can simplify all of that stuff. But then this wouldn't work on BSD. Wait, BSD doesn't have epoll? I didn't know that. Wait, BSD epoll. So just, oh. Here's the free BSD epoll. No, it exists on BSD, at least free BSD, maybe not all BSDs, right? So because there's a lot of them. Or are you guys talking about something else? Like maybe I just actually read the message out of the context. I'm sorry about that. I thought epoll was Linux specific. No, apparently FreeBSD also has that. Like, I didn't know that. It's pretty cool. I mean, to be fair, FreeBSD is trying like really hard to maintain compatibility with Linux, so I'm not surprised that it has epoll actually. So it's part of the standard, like a SAS standard. Yeah, SASI. It's a SASI standard. There is a standard, like a Unix SAS standard. That is literally called SAS. Single Unix, yeah, single Unix specification. I'm not even joking. Like it's literally called SAS. Single Unix specification. All right. So let me commit the thingy-majingy. I think I'm gonna also commit poll try if anyone is interested, right? So I think it's a pretty good example on how to use polls, regardless of like actual feature API or anything, just like a general example how you fucking do that. Right, so let me git ignore poll try. Right, so okay, unspin the echo example by using poll. Maybe we should do the name of the section, right, to specify what we're talking about, right? And I'm going to push that right into the repo. And if you need the code, if you want to explore this code, right, you can find it in here. And obviously for people on YouTube, it's going to be in the description. So yeah, I guess that's it for today. That was a fun stream. The first stream of the year, by the way. I haven't streamed since the last year. So yeah, thanks everyone for watching. Have a good one. Happy New Year, everyone. Happy New Year. And I see you all on the next recreation programming session with Mr. Azos. And I love you all.